All right, this is lesson 4.3, absolute value inequalities. So the goals are I can solve absolute value inequalities. That's why it's called that. And I can identify the special cases when absolute value inequalities result in no solution, infinite solutions, or in a single inequality solution. So that's interesting. Let's see what that looks like. So absolute value inequalities, absolute value you should know because we studied it last unit, right at the end, is a value's distance from zero. So absolute value inequalities ask questions like, can you name a value that is at least x units away from the origin, or zero? Or they may ask, can you name a value that is no more than x units away from the origin? So here's a basic absolute value inequality. It just says absolute value of x is less than or equal to 5. So what that says is x values can't be any more than 5 units away. They must be less than or equal to 5 units away. So if you put 0 right here in the center, okay, then we're talking about values that have to be less than or equal to 5 units away. Well, I can go out 1, 2, 3, 4, 5 units to the right, and those values are less than 5 units from 5 or equal to 5 units from 5. And I can go to the left, -1, -2, -3, -4, negative. So I can go this way 5 steps and reach -5, and every one of these numbers is less than or equal to 5 units from 0 as well. So what we have then is we have this graph that looks like this. These are the boundary values, and all the values in between are less than or equal to 5 units from the origin. So we end up with an AND statement, right? So it says the inequality asks for values that are 5 or fewer units from the origin. So we could write it like this: -5 and 5, and -5, its distance from x's distance from 0 has to be greater than or equal to -5, or less than or equal to 5. So that's what it looks like. That's all the numbers. And I don't actually need the absolute value symbols in there. There we go. So x can be anything from -5 to 5, and that will make its distance 5 or fewer units from the origin. Okay? So to solve them, you just isolate the absolute value expression on one side of the inequality. So that means on the left side down here, I've got to get the absolute value portion, this portion by itself. So I got to get rid of the 2 and the 3. That's what that means. Write the expression inside absolute values in 2 new inequalities. So I'm going to rewrite x minus 4 with 2 new inequalities. One keeps the inequality sign, and the sign on the opposing value the same. So they keep these 2 pieces the same. And the second one switches the inequality sign and the sign on the opposing value. So it's going to make the opposing value the opposite sign, like positive, negative. So this is switching positive and negative, okay, right here. And this is switching the inequality symbol, okay? So you then graph the results to determine if the answer can be written as an AND statement or an OR statement. Okay, so let's solve this one just as an example. So let's see here. There we go. Okay. So we're going to start by isolating, right, the absolute value portion. So I got a -3 from both sides. I'm going to divide by 2. And so here's my inequality equation, my inequality written now with just the absolute value on one side. So at this point, I'm going to break it into 2 inequalities. So inside the absolute value symbols, that number in there has to be greater than 2 units away. So it's got to be greater than 2 units from 0, or it's got to be less than negative 2 units. So think about the number line. If I'm counting 2 units away from 0, I'm going to count 2 to the right, and that's positive 2, so anything greater than that. Or 2 to the left, anything less than that. Okay, but now you got to add your 4 in both cases to finish solving here. So I get 6, and well, that's gone, and then we get 2. So this one says x has to be greater than 6, or x has to be less than 2. Well, let's graph that and see what we get. I know it has to be an or because I can't pick a number greater than 6 and less than 2. So I'm going to put my 6 there and my 2 there, and I get an open circle on the 6, and I get an open circle on the 2. And this can be written as an or statement. X is either greater than 6 units or less than 2 units. Okay. Let's just pick some values that work here, like 7. So if I plug 7 in there, 7 minus 4 is 3, and the absolute value of 3 is greater than 2. Or if I pick 1, 1 minus 4 is negative 3, and the absolute value of negative 3 is 3, which is still greater than 2. So there's my answer, okay? Here, let's try this one. Looks like they've already isolated the absolute value inequality, the absolute value portion. So I'm going to write it as 2 separate statements. One where I keep this symbol and the sign on the 7 the same, and one where I switch the symbol and switch the sign on the 7. Now the step's the same to solve each. You just subtract 8 in both cases. And I get x is less than or equal to negative 1, and I get x is greater than or equal to negative 15. Now what happens if we graph that? Do we get an and or an or? So I'm going to put negative 1. Which one goes on the left? Is negative 15 smaller or is negative 1 smaller? Well, negative 15 is smaller. It's more negative, right? So I'm going to just put negative 15 right here. And then I'll move down over here and I'll put negative 1. So now at negative 1, it says x is less than or equal to. So I'm going to put a solid dot, and then less than makes me shade left. At the negative 15, it's a solid dot also, and greater than negative 15 makes me shade to the right. And so you see this is the graph of an and statement. So I'm going to put my smaller value on the left, the appropriate symbols between them, and the negative 1 on the right, and there's my resulting inequality. Okay? So any numbers between negative 15 and negative 1, when added to 8, are going to give us something that's distance is less than 7 or equal to 7 units away from 0. Okay? All right. You try this one. Okay? Hopefully you did that. Leaving that one the same. Switching that one around. It's a minus 10 everywhere. That's negative 9. That's negative 11. So negative 9, so negative 11 is smaller than negative 9. At negative 11, it's an open circle and it's greater. At negative 9, it's an open circle and it's less. This is an or again, or excuse me, an and again. So the smaller values of the negative 11, there's a no equal to between those, no equal to between those, and there's my inequality that describes the solutions. Okay? So if you pick something between negative 11 and negative 9 and plug it in there, like negative 10. What's negative 10 plus 10? Well, 0. And what's the absolute value of 0? 0, and 0 is less than 1. All right, this one here is ready to split. Okay. Greater than 10, less than negative 10. Looks like a -3 to solve. X is greater than 7. X is less than negative 13. So if I put 7, let's see, I'm going to put negative 13 on this side and 7 on this side. At 7, it's open and it shades to the right, greater. And this one's open and it shades less or left. Well, that's an OR statement. So I'm just going to write OR here and join them together. Okay? You try the next one there. All right. So negative 11 and negative 1. At negative 1, I'm a solid dot. It's shading to the right, greater. And then solid dot at negative 11, and it says less. I'm going to go less to the left. And so this is an OR statement. All right, so there's several possible outcomes when you solve absolute value inequalities. If you have x less than a or less than equal to a, that's going to be an AND statement. Hopefully you notice that. And then if you've got a greater than a or greater than equal to a, then it's always going to be an OR statement. So less than's are ANDs, greater than's are ORs. But if you've got an x is less than negative a, or x is less than or equal to negative a, I hope you know that's impossible, because the absolute value of x can never be negative. You can't, absolute value is never going to be smaller than a negative number, because it would have to be negative, and absolute value is never negative. Absolute value is always positive. Okay? And what if you have x, the absolute value of x greater than negative a or greater than or equal to negative a? Well, that's all real numbers, because every positive number is greater than negative numbers. So since absolute value of x is positive, it's going to be greater than every negative number, and it doesn't really matter. So every number is going to work there. Okay? So no solution versus all real numbers. Let's see that. So absolute value is a distance, and we always measure distance positively. Distance cannot be less than negative 1. So here we're saying distance is less than negative 1, and that is not possible, right? Because distance is always positive. So those values would all have to be negative, and therefore there's no solution. Okay? This question over here, it says that absolute value, which is distance, is greater than or equal to negative 1. Well, since absolute value is always positive, every positive number is greater than any negative. So there's all real numbers are solutions there. So we could write our answers like this: all real numbers. Okay. No solution can be written like this, the empty set. And so let's just look here. Be careful. We're looking for those conditions, right? Because what happens is students just don't even recognize when there's a negative over there, and they just go on and work the problem out anyway. So let's see if we can stumble upon when that happens here on these problems. Well, there's a negative 2, and I got to divide by 2. So x plus 5 is less than negative 1. And this is what we're talking about. This is positive. It can never be less than a negative. Okay? All right. Let's try this one over here. Okay, let's see how you did. Divide by -3, divide by -3. I'm dividing by a negative, so what happens? Switching the inequality to -2. And now here's a -2, and this is positive. So what works? All real numbers work. So we could just write the symbol for the real numbers there. So what would you do? Well, you just shade the entire line. Okay. All right. I think you're ready to try some on your own.